Everybody, I'm Jean-Baptiste Caillau, and I'm very glad to be here. This is a joint talk with my colleagues in the room, Olivier Cots and Alesia Herasimenka. So this is all about optimal control of ODEs and applications to space mechanics. So the idea is that you will look at such a problem. Okay, here we have a Lagrange cost, a standard one, an ODE, x dot equal to f of x of t and u of t. And what you want to do is solve it. Okay, so our core interests lie in several stuff, ranging from mathematical analysis, I would say, numerical stuff, and application, of course. And in the framework of this talk, mostly ones in space mechanics. So let me just give you a few hints about what we did with this package. So the name is optimalcontrol.gl, and let us start with a very basic example of what the package does. So imagine you want to solve this very simple problem, okay, the double integrator that you more or less all know, I think, in with the criterion that will be a simple square of the L2 norm of the control. So x dot is x1 dot is equal to x2, x2 dot is equal to u, which is the control here, okay? And you want to solve this, which means in this case minimizing this integral of u square, right, with a fixed initial and final condition. So with our package, it's going to be, I would say, very easy. First of all, to describe the problem, okay? Just write the following stuff. Of course, you have to use the package here. You also will use an IP models IP-opt, which is the way to call the solver IP-opt. At the same time, to use what our colleagues did, a very nice piece of work on NLP models and AD NLP models, and plot to plot, of course. So the idea is just that you will define the problem in a fashion which is as close as possible to what you would write in math, in fact. Okay, so just saying that the time is ranging from 0 to 1. The state is dimension 2, 1. The control is just dimension 1, and its time is u, by the way. And then you will just give the initial and final condition here, the dynamics, and the cost. That's the definition. Once you're done, you just solve and plot. Let's solve and let's plot. So you see here that you call IP-opt, okay? The linear solver by default is mumps, from our colleagues in France too, okay? So you have not so large number of variable constraints here. It's pretty fast. I mean, this problem is very easy, actually, so you just solve and you can plot, okay? So you can get in the solution with the two states, x1, x2, an approximation of the adjoint, p of x1, p of x2, and the control. A very simple one, which is just a linear one here. Okay, definition, solve, and plot. Okay. You can also save the data for further use and so on. So let us go now to something more in touch with space mechanics. More or less, I suppose all know this famous Goddard problem, which is not so simple a problem, in fact, because even for this particular case, where you want to maximize the final value of height r, okay, we will have several r's, in fact. So you have this second order dynamics again with the control u, Tmax, which is the maximum thrust, and the mass is also varied according to the consumption of fuel. And we'll add a state constraints on the velocity, okay? So V has to remain less than Vmax. Of course, you have also initial and final conditions on the problem. So again, you define the problem. Okay, here, essentially, we also will use ordinary defect since we will use some indirect method, shooting, okay? So we'll use, of course, this very nice package too. So again, let's just have a look at the definition. You have some constant, T0 is fixed to 0 and so on, but just take a look at this. Very similar to what you would write in mathematics, in fact. So again, you define the state. You can name the different components of the state, okay? You just solve once you have defined this problem. Again, we have added some path constraints here. For instance, we even have added constraints on R here, so that's R will remain higher than the initial value r of 0. And we also have this path constraint that I just mentioned on the velocity. The dynamics is a so-called a fine one. You have two vector fields. The control one is F1, okay, that you will be able to define afterwards. And you recognize here the value that I just showed in the beginning when I just defined the dynamics of the Goddard case. So F0, F1, okay, now the problem is completely settled. And again, we just solve, okay. The grid now is 100-point grid, a very raw one, okay. And the idea that once we have solved with the direct code, we will branch the solution to the shooting method. We solve. Again, this is IP-opt, okay. So def solve. You can plot. You see that you have convergence here, quite fast, okay. And here you can have a look at the solution in terms of RV, the state. You also have the mass, in fact, okay. And for instance, you notice here that there is one boundary arc, okay. Afterwards, it's quite easy to analyze the solution to see that, okay, there must be one bound arc, bound plus one, probably one singular arc here, one boundary arc corresponding to this subarc where you activate the constraint on the path, on the velocity, and it looks like you end up with the bound arc, a zero bound arc, coast arc, okay. So bound, singular, boundary bound structure, not so simple, okay, even for this well-known case. So what you will do now, you will, of course, use the structure that you have captured here, okay, to branch the solution to do some shooting. To do this is quite easy to make an inspection, okay, to check, for instance, the value of H1, the Hamiltonian lift, okay, of the vector field F1. When it's vanishing, it means that you probably have either a singular or boundary arc. This is what you get. And you can get a rather precise approximation of the switching times between the several arcs. I will go fast on this, but in this case, it's quite well known that you can use Poisson brackets to compute the singular control, which is control of order 1, okay. This is, in fact, all given by our package. For instance, you can retrieve for free brackets, Lie brackets and Poisson brackets for vector fields or Hamiltonians that you will need here. For instance, to define what you see at this point, which is US, the singular control, its expression, okay, will necessitate order 3 length Poisson bracket. Okay, this is given all for free here, again thanks to AD. In this case, it's forward if. So in the same fashion, you can compute the boundary control, UB, okay. Once you have the control, the maximizing one, the bound ones, U0, which is the zero bound control, U1, the plus one, the singular or the boundary, okay, you will use your OCP and define the flow, okay, in terms of state and co-state, just within one line. Once you have these flows, you can just call them. This will call your favorite Runge-Kutta scheme, okay, just to allow you to define the shooting function in this very simple way. You will go from T0 to T1 using a bound arc, okay. This will be the plus one arc, F1, so the flow of F1. Then you will go from T1 to T2 using the singular arc, the flow of the singular control here. Then from T1 to T3 using the boundary arc, and eventually you will use the coast arc, okay, U equal to 0, with the final flow from T3 to TF. In this case, TF is free. So that's why in the beginning, maybe you had noticed, I'm going quite fast, but still I can go back on this. For instance, with TF as variable, yeah, here TF is not known, okay, so it's a variable. You can add as many variables as you would like, okay. They will be optimized then. Okay, so we have a nice approximation of the initial adjoint state. We have a nice approximation of the switching times. Let's solve, okay. In this case, we will use a nonlinear solve. So the function is here, shoot. We define an NLE, a nonlinear problem probe, and we solve it, okay. So this is a nonlinear solve. I will show you next an example with minpack, but essentially you will have the same kind of behavior. So we retrieve the solution P0, the initial value of the co-state. Okay, this is typical shooting method. The unknown switching times, right, and the final time. Then we can plot again. Okay, this is the result of the solve, which is quite fast here since we have a nice approximation. You see that the shooting is solved up to 10 to the power minus 13, so quite nice. And you see here So in red, the new solution, quite close to the previous one, the direct one, but you see, of course, that you get very nice precision, very neat value for the control, of course, okay? While you had oscillation, not surprisingly, along the singular and the boundary arcs, right? So again, you see these three phases here. Of course, if you have some questions, please feel free. Just before finishing with some solar sailing, another example, not a standard one, which is still a well-known one. This is an outcome of what we did during quite a few years with the French Space Agency and Thales also in South France. Imagine that you want to minimize the final time for the control two-body case. Okay, so this is the well-known equation. Q dot is equal to some mu here for the Earth. Q divided by the power 3 of the norm of the position plus U, which is the thrust, okay, that you will control on satellite divided by the mass. So this is the acceleration of, again, like in the Goddard case, you have a flow of fuel, so the mass will be decreased along time. And we got this constraint on the control U. The target, the typical one, is to have a very low Tmax. Okay, so you want to solve a so-called low thrust thing. So you will notice here that we will solve the 3D case, okay, where you have these nice Gauss equations that we'll just skip, but essentially you will define these vector fields F0, which is the drift, and the control one, F1, F2, F3. Okay, maybe those of you with a good view will recognize these well-known Gauss equations, and the problem and the dynamics is just written in the following way: L0 of x of t, okay, plus the acceleration here, okay, t divided by the mass times the control times the vector fields F1, F2, F3. Okay, Gauss equations plus a term of control U. You want to minimize TF, and you have this constraint, okay, on the control here that we have normalized, that the control has to be in the 3D ball. Okay. Again, we have initial conditions, final condition here, x at TF. I mean, you fix everything but the final value of the longitude, L. Okay, again, you def, you solve. Okay, here for Tmax, which is a very strong thrust because it's easier. Okay, just more or less one turn, and you use this direct code with the IPOP to solve this. Here you see you have just a view of what the package will tell you of what you have just defined. That's a way to check it's all fine. Okay, you see, for instance, that you have defined time, state control. The variable again is TF, which is not known since you want to minimize the final time dynamics and so on. You solve, okay? The solve is quite fast. Here again, we just use a very raw grid, okay? And here is the convergence in a few seconds, and here is just a view, okay, at the semilattice rectum P and so on. Eccentricity vector, the corresponding value for the 3D case, and the longitude here. Roughly, we're going from 3 to 9, which is more or less one turn, a 2 pi length in terms of angle. Okay, and here is the control for this very simple case. It works, it converges, and once you have done this, of course, you can solve to have something which is nicer, in particular for low thrust, and just use shooting to do this. Okay. So again, what you will just pour into the problem is the maximizing control U. Okay, here, Pontryagin maximum principle will tell you that the control is just this simple expression, okay, that you can retrieve in terms of the Hamiltonian lift, again, of these vector fields F1, F2, F3. You inject the maximizing control UR into your OCP, you just get the flow, and the flow you can use it to define the shooting function in a standard way. Okay, you just look from for TF and P0, the initial value of the core state, and for the final time t, again you just use the flow from 0 to TF. Here, one single arc. Okay, at some point it is a simpler case, at least in terms of structure, than the Goddard case. You just solve, okay, using here min-pack, so F solve. It converges very, very easily, and You can do again this kind of thing. For instance, to solve for a much lower thrust, going from 60 newtons, okay, for a 1.5 ton satellite to 0.7. This is already quite low thrust, okay. With this code, you can go down to 0.1 newtons. It just works. Again, there is another means to define the regular flow, which is from the beginning to define the maximized Hamiltonian HR. This will be more efficient in terms of code, but the same kind of idea. So you retrieve the flow again, and you just solve again using a solve. Converges, okay, this is the convergence of the shooting call. And let's just have a look at what you get here. This is a typical orbit transfer, okay. You want to correct the inclination, and at the same time, of course, go from very eccentric 0.75 to a circular orbit. Okay, I will just now lay the floor to Alesia for a few words on solar sailing.
Great. Okay, can you hear me? Yeah, I guess yes. So this is the example which is still work in progress about solar sails. Solar sails are satellites that use light. So this project was in collaboration with ESA, and the idea was to use solar sails in order to go into interstellar environment and to basically leave the solar system. So the idea is that you will use solar assist and solar radiation pressure assist by flying very close to the sun, and then you will achieve a hyperbolic orbit and expels your satellite from solar system. So what I did first was to use some local optimal control laws in order to find some feasible trajectories. But those trajectories are not globally optimized. It's just local optimal transfers. So I will leave Earth, come to the sun, and then I will use these orbits in order to achieve hyperbolic orbit and to expel my satellite. So in order to find the globally optimal trajectory, I will use this nice optimal control toolbox with Julia. So again, we will define the problem in the same way. So here's just the definition with some parameters, optical parameters of the problem, also some space mechanics constants. And then I will just put the inputs from the initial guess that I found using local optimal control laws. And then what I will be doing is that I will define the equations, which are just Kepler equations. And the constraints in my problem will be not to burn the satellite, right? So I cannot go into the sun. So my constraint will be some temperature constraint. This is why I define this temperature function. So then the definition of the optimal control problem is that I have a finite time, because I did some local optimum calculations before, so I have the final time. I have my state, which is just position and velocity in a 2D case. My control is just the angle, because I will control my satellite by changing its orientation according to the sun. And basically my constraint is this one, which is just the temperature constraint. And of course my equations. And the cost which I want to maximize is not like usually we minimize the control, but in my case, because the control is free for me, what I want to maximize is the energy of the orbit. So I want to achieve hyperbolic orbit at the end. So what I will be doing is that I will give the initial guess from the local optimal control laws to my problem, and I will solve it with the initial guess. And then again, plot the solutions. So in this case, I just took a very small arc from my trajectory. I think you can see it here. How can I make it smaller?
Well, you probably can't. Yeah.
Yes. So you can see in red the trajectory, which was the one, doing local optimal control laws. And then I just took a very small portion of it, and I tried to do it using the optimal control toolbox. And you can see already that if I compare the cost function, so this was just to see that the constraint is satisfied. But if I compare the cost function, I already gain some energy. So I have a better results. And then what we can do is to use continuation on the initial condition to solve the problem for the full trajectory. So basically I will be moving my initial condition. Here it's a GIF. which is a bit too fast, I think. But what I will be doing is to move my initial position back to the real initial condition to find the whole trajectory. And again, you can see on the plot that the energy at the end of my trajectory is better than the one found with the optimal control laws. So this is the example for solar sails.
Thank you, Alesia. You can keep the mic. Yeah. Okay, so to wrap up things, the idea with this Julia toolbox is to have a high-level modeling of control problems. Okay, no trade-off between being close to mathematics and have as possible an efficient solve. Okay, again, we use IPOpt, we use fast linear solvers, so no trade-off between the two things. The idea also is to have direct and indirect cause collaborate. They, I mean, no one is better. They all work well all together. We also have a collection of examples. For instance, Olivier just put a very nice example on quantum mechanics here, okay, that you can have a look at. And of course, we're open to contributions. So at the moment, there are ongoing things that we want to implement. For instance, the so-called direct shooting, where you just discretize the control U, not the control and the state. Collocation method too for BVPs and so on. So again, have a look at optimal control.gl. Will be soon on the general registry, just a question of hours, I hope. Thank you very much. C'est toi qui as le micro.
Hi, thanks for the talk. Very interesting. I have two questions. In the past, I solved some similar problem using another package called finite-opt. I'm not sure how it relates to it, but this is specific for optimal control, so
Absolutely,
it's very nice.
Yes.
Very nice.
In finite-opt, in fact, you can do some more stuff like ODEs, PDEs too. Okay, but I mean, it's not I would say as flexible for control of ODEs as what we did. We really wanted to have an abstract thing as close as possible to the way you would write math. Okay, yes. So finite-opt is a very nice piece of work, which is at some point layer above jump, right? Which is absolutely nice. We also wanted to use pure Julia code, okay? Not in fact enforcing some DSL and so on. So for instance, in this case, what you can see, I don't know, for instance, in the Goddard case, so sorry. Okay, we define the vector fields here. Sorry, at some point here. Okay, this is pure this is pure Julia code. We do not compel the user to use some specific way to write the vector fields.
Yes, this was very nice. I saw that. And my second question was, is it possible within this package to define a problem with multiple phases in which each phase will have a different dynamics?
Yeah, sure.
Yes.
At the moment, it is not completely automated, but still it's quite standard to rewrite such a problem, okay? As a problem with several arcs, okay? You can enlarge the dimension, okay? And then you put all these arcs under the same kind of vector, okay? This could be automated at some point with saying that, okay, at the end of arc 1, you are at the beginning of arc 1, so on. So this could be automated. This we have not done yet, but it's a possibility to do so. Yeah, sure.
This is awesome. Thank you very much.
Yeah.
All right. In first place, thank you for your presentation. I think this is a very nice syntax what you have achieved there with the macro, like having done some optimal control in the past as well. Like this looks really nice. So I wanted to ask about in the direct method, what kind of discretization are you using and how you plan to deal with, like, I don't know, if you want to go into mesh refinement or...
Very important point, yes. Yeah. At the moment, it's just a uniform grid, okay? But you can actually pass whatever grid you want, okay? And for instance, I have a simple example here, which is a completely different one from mathematical biology. For instance, you can check here that we solve, okay, get the very raw control, which is the blue one. and we refine the grid in a stupid way, and we just get the very neat one, which is the red one. Okay, imagine that in this case, what you see is a control with fuller in and fuller out. Okay, so you have this nice approximation, and the shooting method would be really lost there. But the direct one, even with a uniform grid, just fine. So yes, you can path whatever grid you want. Okay, at the moment we do not have any refinement process, but I mean the user can take care of this thing. I think it's quite standard.
Yeah, absolutely. And in terms of, so you use like I don't know, a 30-degree for the segments. Do you use like a 30-degree collocation method or what?
Very simple one. We use the trapezoidal rule, which is absolutely robust one. And our experiments with, say, Gauss-Lobato schemes, okay, higher order ones, in fact, just told us that apart from very specific cases, they do exist. Okay, in general, it's just fine to use a larger grid, just with this order 2 scheme, because it's just a very robust one.
Yeah, I mean that matches my experience as well. Like higher order methods, like often are more accurate in some problems, but they are like less robust in that if the problem gets tricky, it's easier for them to.
Right. But still, at the moment, we are implementing higher order Runge-Kutta schemes. Okay, I think that we will add Gauss-Lobato one, just in case. And some people, in fact, from mathematical biology, they do have cases where it's nicer. I mean, at least to have a nice precision on the control. So these cases, yes, it's better, but it's quite rare, in fact.
Okay, thank you.
Thanks. Welcome.
Any other? Yeah.
Do you have also model predictive control tutorials?
Not now at the moment, but I mean, it's quite easy. You just could write your loop, okay, and just change here. I mean, look, in your definition here, okay, it's completely trivial stuff to change your T0 or even your TF if you want to have some sliding horizon or a receding one. You just you just have to write a loop and then to do it, but it's not done at the moment. Okay, but I mean, it's not that complicated to do it, and probably it would be nice to add one example of this kind of thing. Yes, actually, yeah.
I think for educational purposes, to show this in the lecture, this would be quite good.
Right. Actually, we have an example of this case with MPC for marine navigation, so it would be nice to add it here, and it works fine.
Okay,
yeah, right.
Thank you.
You're welcome.
Okay, I think it's time to move on. Oh no, yeah. And let's thank again Jean-Baptiste and
Thanks
Alesia.
again.